When it comes to analyzing collisions mathematically, you will typically, if you look at a textbook or you look online, you'll typically find a set of three equations. One that relates to objects that collide and bounce off one another. You'll find another equation for objects that begin separate, so they're maybe traveling towards one another. Then, after they collide, they stick together and then move as one, such as maybe like a football player tackling another player. You may also see, you'll primarily see a third set of equations or a third equation that describes two objects that are together and then become separate afterwards. So it's like if you were standing on a skateboard with a basketball in your hand and then you toss the basketball to a friend. The ball would go one way, you'd go the other way. And these three equations are usually used to describe the conservation of momentum during these collisions. And I used to teach them that way, but I found that most students tend to get very tripped up by them. They try and memorize these equations, they try and remember which one applies to which situation, and it tends to result in a lot of confusion. So I'm going to present a method you don't necessarily need to use, but I think it's a much more simplistic method. It focuses on the concepts as well. So as you use this, it will hopefully strengthen the concepts. And lastly, it can be applied to any one of those situations I just told you without ever having to come up with, these three equations or figure out which one to use or make a decision like that. If you just use this method, you can give it a shot, and I find that this eliminates a lot of that frustration. It's kind of like a one-size-fits-all method. It applies to every single situation, and there's no need to differentiate between them. So I think the best way to do this is with some examples. So I will go ahead and start with that right now. So let's look at this situation where before I have a mass that has 10 kilograms and a velocity of 8 meters per second. That's what object 1 is traveling at. And it's traveling and is about to collide with object 2, which has a mass of 12 kilograms and no velocity. It's stationary. Now afterwards, the question is basically asking if that object number 2, which was originally stationary, begins traveling to the right at 6 meters per second, what's happening to object 1? What is its velocity? So, is it still traveling to the right? Has it stopped moving? Has it bounced off objects 2 and is traveling to the left? This is what the conservation of momentum and mathematically analyzing collisions will allow us to do. Now, I think the easiest way to do it is to just calculate the momentum, and we're going to look at two different periods. Just like energy, we're going to look at before the collision as well as afterwards. So for object 1, we know the momentum before is 80 because momentum is mass times velocity, and its mass was 10 and its velocity was 8. Object number 2 had no momentum because it had no velocity. So my total momentum for the system before was 80 kilogram meters per second. Now afterwards, we know that the momentum of object 2 will be 72 because its mass is 12 and its velocity afterwards is 6. That gives me 72. We don't know what the momentum of object 1 is afterwards, so I usually just represent it by lowercase p with sub the number 1. So we know there's some momentum, we don't know what it is. Now the key here lies in the conservation of momentum. We might not know what this momentum is, but we know that whatever my total momentum was before for any collision will be the total momentum afterwards. So just like 80 plus 0 had to give me 80, the momentum of object 1 afterwards plus 72, which was the momentum of object 2 afterwards, must equal 80. And that's exactly what I've done down here. Momentum of object 1 plus 72, which is just these two added together, must equal 80. So if I just solve for the unknown momentum, I find that it has to be 8 kilogram meters per second. And if I want to go one step further, I know that momentum equals mass times velocity. So 8, which is the momentum of object 1 afterwards, must equal its mass, 10 kilograms, times its final velocity, which in this case would be 10 times Vf, or V final. If I just divide both sides by 10, I will find that object number 1 after the collision is traveling at positive 0.8 meters per second, or 0.8 meters per second to the right. So this object is still traveling to the right, significantly slower. Most of its momentum, all of the momentum that it had previously has been transferred to object 2, and only a small amount remains. Now the last thing we always need to do with these collisions is just compare the initial and the final kinetic energy. This allows us to determine if it's an elastic or inelastic collision. So if the kinetic energy equals 1/2 mv squared, I'm going to use the same values from before. So 1/2 times a mass of 10 times a velocity of 8 squared will give me 320 joules. Object 2 has no kinetic energy initially because it's not moving. So my initial kinetic energy before is 0. So before this collision, the whole system, both objects, has a kinetic energy of 320 joules. I will go and do the same thing for the second one. Afterwards, 1 half times 12, which is the mass, times 6 squared, which is the velocity. That gives me my final kinetic energy for the second object. And 1 half times the mass of 10 times the velocity of 0.8 squared will give me the kinetic energy of object 1 afterwards. So all I've done is calculated the kinetic energy of both objects before and both objects afterwards using all the information that I found, and then I just total those up. And in this case, you will see that I started with 320 joules. So together, these two objects had 320 joules of kinetic energy prior to the collision, and afterwards, they only had 219.2. So I had less energy over here afterwards than I did before. That immediately tells me that this is an inelastic collision, and some kinetic energy has been lost to things like sound, heat, etc., that dissipated energy. So it's not too difficult, but you can use momentum essentially to figure out how fast or in what direction it's moving afterwards. The only added step would be to compare your initial and final kinetic energies to see if you've lost any energy or in fact it has been conserved. Just to show you how this can also be applied to situations such as this, where you don't have one of them being stationary. You have two objects traveling towards one another. Object 1 bounces off and travels backwards at 2.91 meters per second, and you want to figure out what's going on with the velocity of the second object. Again, if we calculate momentum, prior, 5 times 8 gives me 40, 6 times negative 2, negative because it's traveling to the left, gives me negative 12. So the total momentum before is plus 28 kilogram meters per second, and thanks to the law of conservation of momentum, that must be my total momentum afterwards. Well, we know that my mass is 5 and my velocity afterwards for object 1 is negative 2.91. So when I multiply those, I get negative 14.55. We don't know what the momentum of object 2 is, so I'll just leave that as P2. And just as we did before, we know that negative 14.55 plus P2 must equal that total momentum of 28. And when I solve that through, I find that momentum of object 2 after the collision must be 42.55. If I use my momentum equals mass times velocity equation, I can therefore determine the final velocity. 42.55 divided by 6 gives me 7.09 meters per second. So I found that the momentum lost by this object was gained by the other, and because it's a positive number, it tells me that this object is now traveling to the right with a velocity of 7.09 meters per second. All that's left to do at the end is to very quickly calculate my kinetic energy. So I have two objects, object 1 and 2. Using my masses and my velocities, I can calculate my kinetic energies before and after. You'll notice that neither one of these are negative, even though I have a negative velocity, because energy is a scalar. Direction does not matter. So for energy, I can ignore my velocity. Also, the velocity is squared, so mathematically it cancels out anyway. So we can see here that my initial kinetic energy was 172 joules. Afterwards, I know the velocity of object 1 is 2.91 to the left. I know the velocity of object 2 is 7.09 to the right. Using those values and their masses, I can use 1 half mv squared to calculate their kinetic energies. And you'll notice there's a small discrepancy when I add my totals, but that's more due to a rounding error. You can essentially see they're both about 172 joules. This tells me that the kinetic energy before and after are equal, and I therefore have an elastic collision. So there was no sound, no heat, nothing of that sort. If you didn't physically see this collision with your own eyes, you would never have any idea that it had ever happened or ever occurred. Last, and I'll go through this one a little bit quicker because it's the same process. You can always slow down the video if you want to. But just to show you, I have two objects that are traveling towards one another. After they collide, they stick together and they start to travel as one. So the question then becomes, what direction are they traveling in? How fast are they traveling, etc. Again, I'll calculate my total momentums before. So 20 times 10 is 200. Negative 6 times 15 is negative 90. And afterwards, I know object 1 and object 2 have momentum, but I don't quite know what they are. I do, however, know that the total momentum before has to be equal to the total momentum afterwards. So therefore, the momentum of object 1 plus the momentum of object 2 must equal 110 kilogram meters per second. If I keep in mind that the momentum equals mass times velocity and the objects will be stuck together, it's not too far of a stretch to realize that the mass of object 1 times that final velocity plus the mass of object 2 times that final velocity, and remember these would have to be the same, will equal the 110 that I calculated before. By solving that out, I can find my final velocity of both these objects together must be 3.14 meters per second. And of course, the last thing I'd have to do is check my kinetic energies. I'm not going to go through the whole process. I used 1 half mv squared for each object, using their initial velocities here and their final velocities. And when I totaled up my kinetic energy before and after, I found there was quite a large discrepancy. And by subtracting these two, I could actually find the actual amount of kinetic energy that was converted to sound, heat, etc. And that was because this was an inelastic collision, produced sound, heat, things along those lines. All right, so this is a method that can be used for any situation whatsoever. And all you have to do is calculate your momentum before, your momentum afterwards. And that's always going to allow you to figure out typically the final velocity of one of the objects. And don't forget, you always need to check your kinetic energy afterwards to determine whether or not you're dealing with an elastic or inelastic collision.